So my name is Glenn Anglada. I'm a senior ocean engineering student here at USM. Today I will be talking about my senior design project, which is optimizing and evaluating fused deposit modeling, which is a form of 3D printing for underwater applications. So the first content and the motivation we're going to talk about, so subtractive versus additive manufacturing, and then how 3D printing is growing in the maritime industry, and what is FDM printing. So the project objectives that I wanted to cover are improving waterproofness of 3D printed parts and creating a slicer profile to create those 3D printed parts. Then we're going to talk about 3D printing. So that's going to contain what is FDM, what are the voids within prints, the materials that are typically used for printing, and 3D printers. So the design process of it is going to cover printing the 3D printed end cap, on how easy it was to print and for testing purposes, and then actually creating and designing the pressure vessel. And then we're going to go into the testing. That's going to include the vacuum tests, the pressure tests, and then the results of those tests. And then the conclusion of the project. So we're going to talk about subtractive and additive manufacturing first. So we're going to get into the cost of materials. So if we look here at this graph in the top right, I used two online companies to kind of figure out the cost of the materials. So the x-axis is the number of parts in the order, and the y-axis is the dollar amount for those orders. So what we can kind of see from the graph here is that 3D printing for lower quantity parts is way cheaper than using a CNC machine that is being used for the subtractive manufacturing. This is, as the graph goes down, what you will see is that in the middle, that subtractive and additive manufacturing will become about the same price, and then when we get to larger numbers for large manufacturing, CNC, so that is the subtractive manufacturing, it becomes cheaper, essentially. So, but for in our case, we're using small parts, so 3D printing is great. If we look at the bottom, there's two pictures that just kind of represent the waste of the material that's used. So the bottom left is typically the waste that you'll have for subtractive manufacturing, and the right is what you will have for additive manufacturing. So very little waste compared to subtractive. So 3D printing is growing in the maritime sector. It's used primarily for prototyping, which we can see here in this bottom left. Boat construction, which you can see in the top right, which there's a 3D printed boat that's being produced right now. And manufacturing of parts at sea. So 3D printers, so FDM in general, can be used on a vessel to 3D print parts that need to be recreated at sea. So that's just a really convenient form that we can actually use this technology in. So the objectives. So we want to evaluate and improve the waterproofness of a 3D printed part, specifically FDM. And we want to create a slicing software profile to remove the voids that are within the printed part. So now we kind of get into what is FDM printing. So FDM printing is we use a thermoplastic material that is heated up and then applied layer by layer onto a printing surface. So if we look right here at the top right corner, we kind of can see the path of the thermoplastic that will go through the hot end or an extruder that is then layered on a printing surface, and it'll go layer by layer, and that will create your 3D printed part. So one problem on FDM prints is voids, and this is why they're typically not really used for waterproof applications. As we can see down here on the bottom right hand side, we have the extruder here that is distributing the plastic layer by layer, and it will create these voids in between each layer and surface, and that is what allows water to travel through the parts and makes it not desirable for waterproof applications. So we kind of been using the term of thermoplastic. So really, what is a thermoplastic? So thermoplastics, there's many different types. So what we're going to talk about is PLA, ABS, and PETG. Those are the three most kind of general forms of thermoplastic. So this is plastic that can be melted and then re-solidified onto a printing surface. That is typically what they are. There's other materials, so there's like nylon, polycarbonate, but in this case we're just going to focus on these specific 3. PLA is kind of the easiest to print that you will see. It prints not needing a heated enclosure, so any printer can kind of print it. ABS is a little bit harder to print though. This you need a heated enclosure because ABS has a problem of warping, and that makes it not really ideal to print with. PETG though is what has been chosen for this project. The reason why it's been chosen is because it kind of gives the best of both worlds. So it's easy to print like PLA, and it still retains the strength of what ABS has. And everybody kind of has an interaction with PETG almost on a daily basis if you drink water. So it's used for water bottles, and because of that it is pretty good for use in waterproof applications, since water bottles are waterproof. The other thing is PETG is also recyclable, so it makes it very eco-friendly. So now that the material's been chosen, I need a printer. So with this style printer, this is a commercial grade printer. They're typically very expensive, and I didn't really want to use this type of printer for this project because it has what is known as proprietary software. So what that means is that I can't really go in the settings and change anything that I need, so it's not really ideal for the project. Now we have a hobby style printer here. This is a Prusa MK3S. This is what I'm using for this project. These are relatively cheap printers. You can buy this for less than $1,000 per unit. And it has an open source software, so that is ideal for this project because it allows me to go in and test different things and change according to the tests. So we kind of talked about open source and proprietary here for software. So what actually is this software? So it is known as a slicer. So what a slicer is, it can take a 3D model of an object and convert it into a series of layers for the 3D printer to be able to create a physical object with. So what are these layers that it creates? So this is what is known as G-code. So it is a geometry of the part that it creates a code of, and then that allows your 3D printer to interpret the actual part to use the hardware to print it. So one of the things that you can do with the G-code is you can change different parameters within the slicer software that will then be sent to the printer. So this could be temperature, the hot end, or it could be the layers of the actual print itself. So now that the printer has been kind of selected and we've talked about the slicing software and its sort of its capabilities of changing parameters, now we can kind of go into the design of the end cap. So the end cap was based off of Blue Robotics on one of their end caps for their electronic housing, as we can see here on the bottom right. Blue Robotics is a company that primarily deals with ROV parts, so you can buy these and they're readily accessible. So picking their end cap, I based mine off of. So I chose this part because it was convenient to print, because it's just a circle essentially, so easy geometric shape for the 3D printer to print. It doesn't really need a whole lot of support material, so it makes it convenient and fast to print per test. So after I had the end cap designed, then I needed to create these seals for it. So I used the Parker O-ring handbook to design the O-ring grooves. So as you can see now in the picture of the end cap, now I have the correct O-rings positioned in the grooves that will then be inserted into the cylinder. So the end cap was modeled using Fusion 360. It's just an easy software to use for this purpose. Once the dimensions were determined from the Parker O-ring handbook, then that allowed me to finish creating the part itself. So we're talking about the O-ring dimensions and how that kind of drove the overall dimensions of the end cap. So using the Parker O-ring handbook, so what this actually is, it gives examples of basic sealing elastomers and for static and dynamic sealing, and it kind of gives an idea also on failing O-ring parts, and kind of shows how to minimize that also. So what I did was I went through the book and I went to this graph here because I wanted a static seal on my end cap, so that is a male gland, and I knew the size of the inside diameter of the cylinder that I would be using, so in my case it was 3 inches. So what that allowed me to do was I could go here to this A diameter for my 3 inches, and I could scroll down through, find the 3 inches, and down here across this line it will give me all the other dimensions that I need for the gland. Then I can come back up here and I could look at the radiuses of the gland, and then I could actually look at the cross section of the O-ring and determine how wide the gland needed to be based off those dimensions. So then, going through after the design of the end cap, I had to have some way of testing it. So I had to come up with a purpose-built pressure vessel. So in the beginning of the project, I wanted to test these at 100 meters, which now looking back is definitely far more than what I think I could have ever really got with this. So I backed it down to at least 25 meters for testing initially. I used industry standards for the O-ring, so the Parker handbook, and tolerances for all the hardware for the pressure vessel design. So the pressure vessel was then modeled using Fusion 360 to make sure all the parts fit correctly, and there was nothing not hidden anywhere. What we can kind of view here though is the geometric shape inside of the pressure vessel. So this is designed to allow air to escape the system and to be filled with water. So we're going to kind of talk about that a little bit more on why water was chosen later on. So after it was designed, what Fusion allowed me to do was to run a finite element analysis. So what this allowed me to do, it allowed me to pick the material that I wanted to do. So in my case, I wanted to be see-through, so I picked acrylic. And this allowed me to determine the thickness of the material for the pressure vessel. So as we can see here, this was designed and it was tested within Fusion for 100 meters originally. So the blue, you can see very little strain on the pressure vessel itself. Where the end cap itself, you can see it buckling. Of course, that's because it's the thinnest part of the system, and that's where we expect, it would potentially fail at over the pressure vessel. So this way we over-engineer and we design it to where it's very safe to actually use. So going into how to pressurize the system. So I chose water. Because water is incompressible unlike air, and if air, because it's compressible, will store a large amount of energy, and if there's a crack or a failure within the pressure vessel, that could lead to a catastrophic failure as an explosion with air. Where water, it'll just leak out of the failure spot. So here we have a diagram that's an exploded view of the pressure vessel of all the components. So the pressure vessel will then be pressurized by a hydraulic hand pump that allows me to have more control over how much pressure is being inputted into the system, and that will be connected here to this valve at the end. So now that the pressure vessel has been designed, I needed to actually make the pressure vessel. So the construction of the pressure vessel, I used Fusion 360 to design the tool path that will be used to mill out the pressure vessel. So I chose the cutting bits based off of the geometry of the pressure vessel based on the radiuses of the O-ring grooves that I got from the Parker handbook, and the inside diameter of the cutout that I needed to be removed. So after these tools were then picked, I could use a CNC milling machine. So this is a Haas VF5. This one is at the MRC, which is the Marine Research Center here in Gulfport. And they were gracious enough to help me with my senior project and mill my pressure vessel. So as we can see here, this is the video I took during the milling process of the pressure vessel. This is just cutting out the bulk of the body of it. So then after that process was done, I was left with this blank here with the holes milled, the O-ring groove, and the inside milled out. So I'll show you the completed version of it later on in the presentation. So then I had to come up with a form of testing these 3D printed parts. So the initial tests were done by trying to optimize temperature, layer height, extrusion multiplier, and the vertical wall thickness. So how did I kind of do this? Well, I had to kind of really go through and figure out what these parameters actually did to the part itself. So the temperature will change the actual hot end temperature of the printer. The layer height changes, of course, each layer of the print itself. The extrusion multiplier will change the amount of the thermoplastic, so it changes the volume that's actually being pushed out of the hot end. And then the vertical wall thicknesses are the actual number of walls on the inside and outside of the 3D printed part. So once I kind of figured what parameters I wanted to change, I needed to go into testing. So this, I'm using a vacuum to do all my initial tests. So what I did here, so in the top right corner, this is the hand vacuum pump that I used that is connected to this cylinder here on the bottom right with a vacuum fitting. And then on the vacuum gauge here, what I did was I applied 10 inch-pounds of vacuum. I started a stopwatch. I waited for the vacuum to go to 5 inch-pounds, and I stopped the time. This was recorded for each end cap, and we'll kind of talk about that in a little bit. But that was done through all 12 end caps that were initially printed for temperature and the time. So after those were done, then I could take those data sets and I could put it into a graph to kind of see what the correlation was. So the x-axis here is the temperature that they were printed at. Down here for the legend, we have a blue, orange, and gray. So these are the 3 different layer heights that were used for the test. In our y-axis here, this is the time that the parts were for the leak down from the vacuum. So if we look at the graph here, we can see that the orange here at the top, so that is our 0.2 layer height, kind of gave the best result at 260 degrees C. So what I did was I took this end cap as the winner of this, and I then went to change the extrusion modifier as the next one. So this end cap here only lasted about 2 minutes and 33 seconds. By changing the extrusion modifier, it went from 2 minutes and 33 seconds to over 3 hours of holding the vacuum. So that is exponentially increased the amount of time it could hold a vacuum. So then that's kind of the best end cap that I've tested with that. So that was kind of the first one that was used with the testing for the actual pressure vessel itself. So now that I've had these, then I could go to testing with the pressure vessel. So in the image, this is just the completed version of the pressure vessel. So the pressure tests were done to determine how fast the system would lose pressure for each end cap. So the system was then pressurized to 50 psi. And the time was marked at every minute in increments to determine what the gauge read, and then that was written down. So as we can see in this picture, this is the whole entire system. So the arm here, that is what allows me to actually apply pressure to the system. Then it comes out of this black pressure line, which then will go into the pressure vessel itself. By using in here in the reservoir is filled with water, and that will push all the air out of the pressure vessel, which then comes out of this tube back into the reservoir, which then will pump water through it. Whenever I'm ready to start testing, I will then close this valve, and that will pressurize the system. So because, like I was talking earlier, with using Fusion and doing a finite element analysis, this allows me to engineer the actual pressure vessel to be safe. So it can be picked up after it's pressurized, and then it can be visually evaluated for the end caps where there might be leakage. So if we look here at the red arrows, so those are pointing to 2 spots where water is being pushed through the end cap. And this is of course where the system is leaking. So once these tests were done with the pressure vessel, they were recorded, and then they were put into a graph so we can kind of see the decay of the system of how it's losing pressure. So the blue test here is the best end cap that I had that held a vacuum for over 3 hours. The orange here for test 2, so that is the end cap that was the worst for the vacuum, to kind of give a really good comparison. So it was done over our x-axis, which is time in minutes, and then our y-axis is pressure in psi. And we can kind of see that there's a huge difference in the two tests, and that really kind of shows that the extrusion modifier played a really big part in actually making it hold in the system. So the conclusion. So the results suggest that the right plane parameters can reduce the voids within 3D printed parts. And the extrusion multiplier appears to have the greatest impact over all those parameters. So now it's just trying to figure out, how much more we can push the extrusion modifier to make the test better. So further testing is required for that to find a more optimal parameters for waterproof 3D printed parts. So thank you, and any questions? Yes.
What gave you the inspiration to do the pressure test?
So initially, I have always kind of done stuff with 3D printing. I started off with a hobby, and then I just kind of got addicted to it. And I knew for my senior project, I just wanted to do something with it. And it's not used in waterproof applications like I was talking about earlier. There's other forms of 3D printing that is more suited for that. So I wanted to see how far I could push the material before this application, and I needed some way of testing it, so that's why the pressure vessel was chosen.
I got a question that is more for future referees.
Okay.
How did you get people from the MRC to help you?
So I work at the MRC.
Okay. But if we didn't work,
He's one of the people. He's one of them
yeah,
people.
but if it didn't work there, would we still get help?
So technically, no. You would have to pay. So right now, how it's kind of, they have two different pay rates. There's outside of USM. There's internal for USM. But there is talk of trying to fix some things for students.
Yeah, the idea is definitely to make the MRC available to students, but we have not come up with a very easy solution just yet. But if you need the MRC for your project, there probably will be funding available, which you then can just pay the MRC to people that are using to do that.
Yep.
I have a question.
Yes.
Could you change the pattern? Like you showed that these are all parallel to each other when you're laying these filaments. Can you just go this way and then this way?
So, let's see here. Let's go back. Are you asking about like the picture where I showed the voids and stuff?
Mm-hmm. Yes.
So these. So in this picture, it doesn't really necessarily do justice to how it is. So typically, so like with my printer, whenever it creates this G-code from the slicer, Prusa slicer will turn, and you can change at least in Prusa slicer, you can change this. It allows you to rotate each layer by 90 degrees. So you can change that to where all these aren't one direction within the print. Like one layer, they'll be that direction, and then the next layer, they'll be 90 degrees, and they'll keep rotating perpendicular to each other, is how the default is. So this picture is more to kind of demonstrate, hey, these are what the voids are and how they're kind of formed within the part. Yes.
What was the reason why that capstone leaking?
Yes. So once water kind of finds one of these voids, especially with pressure, and gets pushed through, it will find its way through and out the other side.
Then, have you tried to rate your samples according to the IP?
So that is something we were kind of talking about at the end. Obviously, I didn't have enough time to do it, but I wanted to kind of create a custom IP chart to this where we were correlating the amount of vacuum time versus the amount of time it was actually taking for water to seep through the part. So that's kind of what we were talking about trying to do at the end. So pretty much like an IP chart, but kind of a specific one to this case.
The GIP glad IP.
Yeah.
Okay. And then you showed in the test results, can you go like the first slide that you have for the test results? Go with the graph. Yeah. So this is the time it took for printing, or what is the time?
No, so what this is whenever I use the hand vacuum pump, I apply the 10 pounds or inch pounds, and then I started the stopwatch. So each data value here is the amount of time it took to reach from 10 inch pounds to 5 inch pounds.
Okay, that was our question. Are these the time that it took for print, or the time the vacuum to reach? So I think
Time for the vacuum to go from 10 to 5.
Why do you think the 0.2 layer height outperformed the 0.3?
So from some research that has been done, not by me, but by others, suggests that with the it's kind of weird because 0.3, you can kind of assume that the voids are going to be bigger within the layers. But then that would also mean that the 0.15, which the blue here, should theoretically outperform both of them, but it doesn't. So I'm not actually 100% sure. So that's a really good question that probably needs more research done on.
maybe it's porosity. When you have smaller, it means that you have smaller voids, but still you have more number.
Yeah, so that could be also where we are shrinking the voids, but it is increasing the number of the voids. So 0.2 probably just gives that happy medium to where it's this overall area of the voids are just smaller and there's less of them than the 0.3.
Last question. Have you tried to take a picture in the microscope?
No, I have not. I have not. There's no picture in here, of course, but there was a paper that I was referencing that sort of actually added the extrusion modifier to my list of parameters to change. And they have X-ray images of the 3D printed parts. So you can actually see as they increase the extrusion modifier, the voids are actually shrinking to almost nothing. So it becomes literally almost a solid piece of plastic with a very high extrusion modifier. Dr. Vaughn, do you have a question?
Yeah, follow-up question, but I can ask them. Maybe other questions.
Any other questions?
Well, if there are no other questions, I'll ask you questions. So 0.15 is the worst there. Have you computed how many layers for your part? Per layer height?
So in the slicer, when you slice it at whatever particular layer height, it will tell you the N number. So I don't have those numbers, but I can get those numbers.
It would be cool to look at the porosity that way, although it's really difficult without having the size of the openings between the layers.
Yeah.
That gives like a tentative answer to this question.
So you definitely made big improvements in terms of how waterproof your parts are from just the default settings in the slicer. However, it's still not waterproof.
Yes,
so
no.
Just in your estimation, do you think you will be able to fine tweak it enough to actually get it waterproof? And if not, can you do something else, maybe some post-processing or something to get it to be printed part ultimately to be usable in underwater applications?
Yes, so with this form of testing for my specific case, we still have a lot of parameters and variations of those parameters that we can test. So I would like to say yes, but obviously, it depends on the overall testing. It would be nice, but to answer your other question, part of the question about post-processing, yeah. So the inside or the outside of the 3D printed part, depending on where the dimensions are most accurate, we can apply like an epoxy sealant to it that would encase the inside, would not allow the penetration of water through the part. So we can do post-processing like that to actually waterproof the prints. So that way it would seal it. Yes.
Follow up to that. So if you use epoxy, actually, then would you use your system and the testing method to see not leakage but breakage, to see what pressures that the part actually can withstand?
Yeah, so it's a good question. So unfortunately, of course, in my case, I didn't really focus on the structure integrity of the parts. But there has been testing done, of course, for the actual strength of the part and like correlating to infill, how many wall thicknesses there are and all that other stuff. So that would then be probably applied to it, and you have to figure out, you know, how much strength it would take to break the part and how deep that correlates to. But yes, post-processing first, you know, and then you could essentially apply this to figure out how deep it can go before the part ruptures.
I have one technical question, I guess. So you're running your 3D printing business. Right now you're obviously competing against the rest of the world, and I would think that being able to kind of be the one 3D printing job where you can do underwater safe prints that set you apart quite a bit. So just your feelings, is something you still try to pursue, or how do you feel about it after you've done all those tests?
Yeah, it's definitely something I would still consider to pursue, even after I graduate, to kind of push this and figure out how far I can get it to go, because that's the overall goal. With further testing, I think we can definitely improve at least water resistance of the parts. Might not make them waterproof, but we can definitely make them water resistant up to a certain depth, like an IP rating. For like your cell phone, it's like, you know, you can put your cell phone in 3 meters of water for 30 minutes to an hour, and we could probably do something like that with these parts. Especially because it would be convenient to print the part and then just use it right then and there versus having to go through a post-processing like you have to now. You might have to wait for whatever epoxy or material you want to use to cure or harden or whatever nature. So.
Anybody else?
Do you wish you had more time?
Oh, absolutely. Yeah, that is definitely one thing I have learned through the 2 semesters of project and design is definitely time management of projects. You learn very fast, even when you have a set time set out for everything, where it's a perfect schedule on paper. But stuff happens, unfortunately, and gets in the way of that. And like with the milling process of the pressure vessel, actually, I had to wait almost 2 to 3 weeks later than what I anticipated actually having it done, due to issues at the MRC with the machinist having to be out and whatnot. So that, of course, set me back.
And did you do the last test on the parts?
No.
Yesterday? Today?
No, I haven't done any new testing from that. I actually was excited for Dr. Mall's test.
Yeah, but it was very much the last minute, and it always comes down to wire.
Yeah, no, time management is one thing you definitely learn with projects and design, and how things interrupt that time management. Very much so.
So I have 2 more questions. One, now that we're on this slide, so you said the extrusion multiplier actually made a huge difference, that the vacuum hold drastically increased from 2 minutes to 3+ hours, right? So does that parameter control the speed of the layering, that it goes slower and more material is laid down, or is it literally the amount of material coming out of the nozzle at a constant speed?
So it controls the amount of material at a constant speed. So it doesn't slow or increase the printing time. All we're doing is changing the volume of material coming out of the hot end. So that's kind of the nice thing about a slicer software. So it kind of will take those parameters and it calculates out. So you can tell the printer, hey, I want you to move 50 millimeters a minute or a second, or whatever setting you want to use within the slicer, and then it will take all your other parameters that you change and then calculate it out to what it needs to do to be able to move that fast. So no, it doesn't really have the slicer software compensates for that, so it will move at whatever speed you tell it to.
So that speed can be another parameter?
It could be. So to kind of go a little bit more into your question, so there probably is a certain point to where, of course, the volume of material that you're moving, if you're going too fast, for instance, and it's trying to push it out, it probably could cause the print to fail. You know, same thing if you're moving too slow and it's pushing out too much material at a time, it could also fail. So there's probably a sweet spot in between the actual speed I'm choosing versus how much it's actually pushing out of the hot end. So of course that's even more testing too that can be done to figure that out.
So my last question is to help the rest of the audience here, what would you consider your main challenges and concerns throughout this project?
So, well, the whole thing's been a challenge, of course, because you're having to come up as pretty much like a project manager and figure out answers to questions that Dr. Yates and Dr. Moll asked throughout the 2 semesters. But definitely in the beginning, picking 2 large aspirations for the projects. That is something to where it's really easy to go, oh yeah, that wouldn't be too hard to do within a year. And then you kind of start, you're like, yeah, this is like really going to be time consuming and really tough to do within that time. So that's definitely one of the really big constraints. Like, obviously I wanted to do 100 meters in the beginning for testing, but found out very early on during the project that probably wasn't even remotely achievable right now. So I lowered it to 25, which that's still a pretty good stretch too.
Not only do you just want to print your parts, you also want to build an entire ROV.
Yeah, so that was initially the original project idea was to actually design and build an ROV out of 3D printed parts, which if like this for FDM, for instance, it's already been done, it probably wouldn't have been too bad a thing to do. Or if I would have used a completely different technology in 3D printing that already gives waterproof results, it wouldn't have been too bad. But yeah, trying to combine all this and then on top of building an RV, yeah, that would have been insane.
Right, if you have no more questions, then that was off. And I think I can safely say, so probably walk.
I'm hoping.